Hey, welcome back, ladies and gentlemen. We are going to start your review for Unit 1 today. So we're going to go through, review all the different units that we've learned so far this semester. That way, when you take your final, you don't just straight up fail that stuff. You know what I mean? It's worth a lot of points. You don't want to fail it. And you kind of want to make sure you still remember what you learned. Otherwise, why'd you learn it, right? Do you think you can just forget everything I tell you? That's not cool. So we're going to go through, we're going to review Unit 1. Every single lesson has one, maybe two slides. I think there's only one lesson that has two, and it's because it's got graphs and equations and it didn't quite fit. But should be pretty straightforward. We're just going to review how to do all the most common problems from each type of, what am I trying to say? From each lesson, of course. And then you'll do a little review. Right? Sounds fun. Thanks, Mr. Botton. I love reviews. I know, kids. All right, so the first lesson you learned was composite functions. And what that means is you're going to put a function inside another function, right? You're going to just jam it in there and simplify. So before I start just showing you the two examples, keep in mind that if you see f of g of x, right, that's a parenthesis. This notation means the exact same thing as this notation. This is the same thing. Whatever the second function is, that's the inside function in this type of notation. So you might see it either way on your test or your review or whatever you're going to do. Just remember these are the same thing. I wrote them in this notation down here. And that's just because this symbol thingy right there is kind of hard to make on a computer. So, you know. All right. So we've got two different types of examples here. Let's go through them. If we want to find f of g of 4, what's important here is that they told us the number to plug in. So there's two different ways we could do this, but we're going to do it the easier way, obviously. So one way you could do this is take the whole g function and plug that thing into all the x's in the f function. So you would take 2x minus 3, plug that into the x squared and to the x on the negative 5x, simplify that, and then plug negative 4 into whatever that is. That's the hard way to do it, and that's the way you would have to do it if this were an x instead of a 4. But it's a 4, so let's do it the easy way. So the easy way is plug the 4 into the g function right there, simplify, and then whatever number you get after you simplify, plug that number into the f function. Okay, so let's start by plugging our 4 in. So we have 2 times 4 minus 3. So that's 8 minus 3 is 5. Now we take that 5 and we plug it into the f function. So we're going to have 5 squared minus 5 times 5 plus 6. So this is 25. This is minus 25. And this is plus 6. So these cancel, and our answer is 6. There you go. Easy. Composite functions. Now, this one's a little bit different because the f is on the inside. So that means we're going to take the whole f function and plug it into the g function's x. We don't have a variable inside here. So what that means is that we need to just plug the function in, and we're not going to get a nice number like this. We're going to get an equation, and that's fine. So the way I'm going to do this is I'm going to write out the g function, and where the x is, I'm going to put a big set of parentheses. So we have 2 parentheses. Make sure you give yourself some room, minus 3. Then we're going to take that f function and put that in the parentheses. So we have x squared minus 5x plus 6. Now we need to simplify this thing. So we're going to distribute our 2. So we have 2x squared minus 10x plus 12. Bring down our minus 3. And then just combine our like terms right there. So we have 2x squared minus 10x plus 9. There we go. And then this is g of f of x. There you go. Perfect. Cool. There you go. There's composite functions. basically you're just plugging functions into other functions. It's substitution, so it should be pretty familiar to you. All right. The next thing we want to talk about is determining the symmetry of a function. And this is where we're going to have 2 slides. So we'll talk about equations first, and then we'll talk about some graphs. So for the equations, here's the formal math definitions. For something to be even, f of x has to equal f of negative x. And all this means is if I plug in a number, if I plug in that same number but negative, I should still get the same answer. So a good example to look at is f of x equals x squared. This is an even function. So if you plug in 2, 2 squared is positive 4. If you plug in negative 2, negative 2 squared is still positive 4 because negative 2 times negative 2, a negative times a negative is a positive. So if I plug in the positive 2 or the negative 2, I still get the same output. That tells me it's even. Of course, that's not necessarily like a formal proof that these two things are even. You know, if you're like one of those college kids sitting there like, that's not technically correct. Okay, go blow it out your butt. It's good enough for high school, right? For odd, it says f of negative x equals negative f of x. What this is saying is whatever f of x is, if I plug in the same number but negative, I should get the same answer but negative. So let's look at an example. If we look at x cubed, if we plug in 3 times 3 times 3 is 27. But if we plug in negative 3 times negative 3 times negative 3 is negative 27 because these two negatives cancel and we still have one left over. So if you plug in the opposite sign input, you get the same output but the opposite sign. And that's what it means to be odd. So for polynomials, these things, there's a really nice pattern or rule that you can follow. You just look at the exponents of all of your terms, and those will tell you if your function is even or odd. For it to be even, all the exponents must be even. Even, let's write that down in words. Even, all exponents are even. Okay. Same thing for odd. It's just, if it's odd, all the exponents are odd. Cool? Okay. So if we look at these, our exponent here is 3. That's an odd number. We don't have an invisible exponent here, so it's an invisible 1, and 1 is an odd number. So this function would be odd. Here we have 6, which is even. We have 4, which is also even. Here we don't even have a variable. So what that means is we have x to the power of 0. 0 is an even number. So this is an even function. You might want to remember this thing for the rest of your life. If you have a number by itself, it counts as even because it's x to the power of 0. And then lastly here, we have 2, which is even. We have 1, which is odd, and then you don't have to keep going. Once you see that you have both, this means that it is neither of them. It's not even and it's not odd. It's neither. It's not either one, right? Not either, neither. Cool. All right, cool. So there's 4 equations. If you have weird equations, so let's say you have like f of x equals the absolute value of x minus 7. If you don't know what this looks like, go type this thing into Desmos. Or if this is the year like 2030 and this is super out of date, go type this into whatever the cool free graphing calculator online is and look at a picture of it. You're going to say, how will I know if it's even or odd by looking at a picture? Glad you asked, children. So if we are looking at a picture of our function and we want to know, is it even or odd? For something to be even, what that means is that it has to have reflectional symmetry. This might not be a real English word, but we're going to pretend it is. I think there might be two M's in symmetry also, but we're going to pretend there's one. You have to have reflectional symmetry across the y-axis. So what that means is if you took your graph and you fold it on the y-axis, the left side should exactly line up with the right side. So if I took this thing, folded it there, this would go here, this would go here, this would go here, and it would all line up perfectly. So this one is definitely even. Okay, check mark. Cool. For something to be odd, it has to have what's called rotational symmetry. And what that means is if you take your graph and then you rotate this whole thing 180 degrees. So you flip it, you don't flip, right? We're not taking it and going, that's not it. Never mind, I can't draw flipping. You're not flipping. You're not going to take it and flip it over. You're going to turn it. If you take it and rotate it 180 degrees, the upside down version should look 100% exactly the same as the right side up version. So let me trace this. And now if we take this and we rotate it all the way around, there you go. It looks exactly the same. Ignore this piece. This is me not being able to draw straight lines. This is not imperfection in the math, right? So if you can take it and spin it 180 degrees around and it matches exactly, that means it is odd. Let's maybe go look at an example of not being odd that might look odd. If we have a graph, here, let me get some nice lines. Let's make some nice lines, shall we? Nice line, bro. Okay, so we take this thing, we draw a nice line. Let's even look at the same graph, right? And we'll just do it that way. That looks kind of like butt. Let's try it one more time. That looks a little nicer. Okay, so, whoops. So we just take that same graph and we slide it down a little bit, and then we're gonna flip this thing over. So let's group that. Let's draw our copy over the top, and we're gonna rotate the original graph. If it's gonna be odd, it has to look exactly the same. So we rotate this thing. And now a lot of you guys are gonna say, yes, it looks exactly the same, and you're wrong. Here, the original graph, the red one, this crosses on the negative side of the y-axis. Once I rotate this, the purple one crosses on the positive side. That's different. Just because it's the same shape doesn't mean it's 100% the same. Has to have all the exact same x-intercepts, has to have the exact same y-intercepts. Everything has to be exactly the same. So if we rotate it and it goes from being on the bottom to the top, that's different and it's not odd anymore. This one would be neither. Okay, glad we talked about that. Moving right along, we need to talk about what makes something a function and what makes something a one-to-one relationship. We're having a one-to-one correspondence. So to be a function, it has to pass the vertical line test. So vertical line test just says if we take a vertical line, let's see what color we want, bright green. We take our bright green line and we scan the graph. It doesn't matter if you go left to right or right to left, but as you scan your graph, it can never touch more than one time. If it touches the graph in two places at the same time, that's bad. That's too much touching and it didn't consent to that. So scan, touching once, touching once, touching once, still touching once, still touching once, always touched once. So this, we would say, this thing is a function. Okay. If we want to check if something is one-to-one, this is kind of like the inverse of being a function. It just means that it passes a horizontal line test. So let's go make a horizontal line. What color do we want now? Teal? Or is that cyan? I don't know. And we scan this thing vertically. It doesn't matter if you start at the top or the bottom, it's the same deal. Scanning, touching once, touching once, touching once, touching 3 times. Look at this. 1, 2, 3. This thing is not one-to-one because it fails the horizontal line test. It touches too much. This is bad. So don't do that. Okay? So this graph is only a function. It is not one-to-one. Let's go look at this one. So if we do our horizontal line test, not touching, that's fine. It doesn't matter if it doesn't exist over there. But here, oh no, we're touching 2 times. 2 touches is bad. So this thing is not a function. Not a function. Okay? That doesn't mean it's not one-to-one though. It could still be one-to-one. So let's check that. Vertical line test. Let's maybe make our horizontal line a little wider. There we go. Drag it. Touching once, touching once, touching once, touching once, touching once. It always touches once. So this graph would be said to be 1 to 1. Check mark. It does that, but it's not a function. If something is both, we would call that a 1 to 1 function. And if it fails both, fails both, so that it's neither, we would say that it's just a relationship. No. Hold on. Spelling. Whoops, forward one. Relationship. There we go. I got a little ahead of myself. I missed the shun part in the middle. So this is only a relationship. It's not a function. It's not one-to-one. It's just some weird equation that someone found laying around. Okay. An example of something that would fail both would be like a circle or an ellipse in the conic sections that we just learned. Right? Where's all my shapes? Come on, shapes. Let's get a circle. Right? So if we look at a circle and we hit this thing with our horizontal line test, it touches twice. If we try a vertical line test, it touches twice. So it fails both of them. So circles are just relationships. They're not functions and they're not one-to-one. All right. So now we need to talk about inverses. This was, I believe, section 4, if I'm counting correctly. So there's 2 types of inverses you need to worry about. You need to know how to find the inverse of an equation, and you need to know how to find the inverse of a graph. So for the equation, you're going to swap the positions of x and y, and then solve for y. So you're going to say, there is no y. All right, well, don't get your boxers in a twist or your panties in a twist or whatever sort of under chonies you wear. Just change this thing into a y. There you go. Now there's a y. So we're going to swap the position of our variables, and that's going to become x equals y plus 1 squared minus 3. Cool. And then we're going to solve for y. So the first thing we're going to do is add 3 on both sides. These cancel, so we have x plus 3 equals y plus 1 squared. Now before we can move the minus 1, we have to free it from the parentheses by getting rid of the operation outside. So to get rid of the squared, we're going to take a square root of both sides, like that. So the square root cancels the squared, and here, because we're the ones doing the square root, you have to put a plus or minus in front of it. So plus or minus radical x plus 3 equals y plus 1. And then we just subtract 1 on both sides. Because this stuff is in a math operation, you can't subtract the 1 from the 3, so we're just going to put it at the end. So this is plus or minus the square root of x plus 3 minus 1 equals y. And then for completeness, you should change your y back to the inverse of f of x, just to show us that it's the inverse, because the y doesn't really tell us a whole lot there. All right, so that's how you do it with an equation. You just swap the x and the y and then solve for y. If we just give you a graph, what you need to do to try and find the inverse of this is find some ordered pairs that you can read off very precisely. You want to know the exact ordered pair. So this ordered pair, that one sucks. It's not on the grid. It doesn't, it's hard to read. What is that? Negative 3.2. Yeah, I don't even want to speculate. I'm so appalled by that, right? Ugh, gross. Find easy ones. That one looks great. That one and that one looks great. That looks like a good one. That looks like a good one. So grab a few. You probably want at least 4 or 5. The more curved your graph is, the more points you should shoot for. So this one is -1, -3. This one is 0, -2. This one is -2, -2. This one is 1, 1. And this one is -3, 1. Now what you want to do is take all these ordered pairs, and we want to reverse the order of the numbers. Don't change their signs. You're going to leave the signs alone, but you're going to swap the numbers. So -2, 2, switch them, it's still -2, 2. So -2, -2. That point isn't going to move. -1, -3 though, that's going to flip to -3, -1. So -3, -1, that goes right there. 1, 1, that point doesn't change. So we'll put that one back. 0, -2, that changes to -2, 0. So -2, 0 goes right there. And which one did I miss? This one. -3, 1 turns into 1, -3. So 1, -3. And there we go. We have enough to kind of get a good idea of the shape of the inverse. All right. So I think that's pretty straightforward. Just make sure you don't change any signs. The signs stay with the numbers. So, all right. Whew. Now we need to talk about increasing and decreasing and constant intervals. So we want to know increasing. That means slope is positive. Decreasing means the slope is negative. And constant means the slope is 0. That's actually the symbol for null, but c'est la vie. All right. So what you want to do is you want to basically take your pencil, right? What do pencils look like? That? Something like that. And then you got like an eraser. So you're going to take your pencil. Dang, is that all? Ah, shucks. I thought it was one piece. Let me make it one piece. There we go. Group that thing together. Okay. And you want to hold your pencil parallel to the graph, right? So it lays on it. And you want to ask yourself, is it pointing... Whoops, that's the wrong button. Is it pointing up to the right, down to the right, or is it flat, straight, sideways? So for this section here, pencil is pointing up to the right, up to the right, up to the right, and then it slowly rolls over, right? It's going to continue rotating this way until we get to that spot right there where you could balance your pencil horizontally on the point and kind of teeter a little bit and go, but then it would balance. So this whole section here, we would say is increasing. Let's do increasing in red. We'll do decreasing in blue, and then we'll do constant in green. Actually, let's do decreasing in purple so that it's not the same. All right. So technically right here, our circle is constant. It's perfectly horizontal, but I don't think in algebra or in pre-cal they really care about that. This has like a special name in calculus. It's a critical point, but I don't know that they care about your critical points technically here. So what you care about is where is this increasing section? So we're going to write down our increasing interval. We'll write down our decreasing interval. And we'll write our constant interval. So this increasing interval, it starts over here at an arrow. So this means this thing is going left forever. So left forever would be negative infinity. We are only writing stuff from the x-axis. We do not give a hoot about how far up and down it is. All we care about are the x intervals where it happens. So our increasing interval starts at negative infinity. So we're going to put parenthesis because you can't ever touch an infinity. 2, it continues to increase till it gets right here, and that lines up with negative 3. All right, so it's increasing from negative infinity to negative 3. We don't include the negative 3 because technically right at the top, we're not going up anymore. You're standing there at the top. Your pencil stays level there. All right, now we're going to keep moving along. Here, our pencil tips downwards and is pointing down to the right. It gets steeper, 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 and keeps going down. This whole section is decreasing. We have a negative slope here. So this section would be purple. This weird kink here, don't worry about that. Math can get a little kinky sometimes, but we won't hold it against it. So we'll pretty much just ignore the tip there. So we want to know, where is it decreasing? Well, it started right there at the top. This is still lined up with negative 3. And then it goes to right here. This is lined up with 0 on the x-axis. So from negative 3 to 0, our graph has a negative slope. Moving right along, grab our pencil again. Now this whole section is flat. So this whole section right here is constant. Come on. Constant. So we just want to know, where is this? So it lines up with 0, lines up with 1, 2, 3, 4. So our graph is constant from 0 to 4. And then here we have another increasing section because our pencil is going to point up to the right, and it just stays that way. And it goes to a arrow. So this section would be increasing, and the arrow says that we continue on until infinity. So for increasing, we need to add another section. To attach a new section, we kind of need our sticky glue to attach it. So we put our union. This section goes from right here at 4, and then it continues on for forever, and we know that because there's an arrow, so we give it an infinity. And then that's how you should find your increasing, decreasing, and constant intervals. All right, very last thing we need to talk about for Unit 1 is the average rate of change. So average rate of change is exactly what it sounds like. It's not how much you're earning every single second of every day. It's just if you were going to earn it at a constant rate, so the same amount every day, about how much do you need to shoot for every single day so that you get to where you want to be at the end. So that's what we mean by average. So before we read the question, we need to remember the equation for the average rate of change. And it can be written as either change in y over change in x, or y2 minus y1 over x2 minus x1. Or you can think about it like final minus initial. All right, so here's our formula. So we need to go find two ordered pairs on both ends of our function. So if we have a function like this, and let's say our graph looks like this, and I want to know what's the average rate of change on this bendy thing here. I need to know the endpoints. I need to know where did I start and where did I end, and then we'll plug these two ordered pairs into this formula to figure out our average rate of change. All right, so let's go read our question and find some ordered pairs. Stephen purchased a home in 1994 for $135,000. Stephen was able to sell the home in 2002 for $168,000. What was the average rate of change in the price of the home? So we want to know what is the change in price. This triangle is the Greek letter delta. It's like the math symbol for change. Okay. So we want to know what's the change in price of the home. And we want to know that as dollars per year. All right. So every year, about how much money did Stephen earn by owning a home? Right? It doesn't seem like a lot of work to earn that, but you know, we won't judge. So let's start by finding our ordered pairs. Here is a starting time, and here is a starting price. So we can turn that into an ordered pair. So in 1994, his house was worth $135,000. Right? And this comma is part of the number, not part of the ordered pair. Maybe I'll erase it for clarity. All right. Then we need to figure out the ending value. So in 2002, his home was worth $168,000. So 2002, and we have $168,000 dues. Now we're going to just plug these into our formula. So 0.2, where it says y2, x2, that's usually your final. So we'll call this one 0.2, and then our initial, or our starting value, we'll call that 0.1. So our formula is y2, so we go to 0.2, take the y value, 168,000, minus, this minus sign is part of the formula. It doesn't revolve around what sign this number is. y1, so 0.1, here's y, minus $135,000, over x2, so 0.2, here's our x, 2002, minus x1, 1994. All right, and now we just clean this up. So 168,000 minus 135,000 is how much? 33,000? Divided by 2002 minus 1,994. This is 8. And then we'll throw this thing into a calculator, which I totally 100% done ahead of time so that I don't need to aimlessly just keep talking and pontificating and teaching you new cool English words while I type it into my calculator. I would absolutely never do that to you guys because I am prepared ahead of time to tell you that the slope is 4,125. And to get the units of this, it's the units of the top, so these are dollars, and then per or over the units of the bottom. So it's $4,125 per, which is what the little slash means, year, because these are years. All right, and that's everything you learned in Unit 1. So hopefully you remember all that. Hopefully you remember that from like your kindergarten math class, right? But if any of this isn't clear, if you're struggling with the formulas, if you're struggling with adding, I don't know, whatever you're struggling with, go tell me about it on the WebEx. Say, hey Barton, I'm struggling, dog. I need some help. Listen, that was a great video, but I need some assistance. Go tell me. All right, I'll see you guys later.